Now that you know what models are and how they can be conceptually developed, it is time to move on. In this course, you will learn how to effectively translate your conceptual model into a set of mathematical equations. Remember that we recognize 4 modeling steps, with first the model formulation, second retrieving solutions, third applying, and fourth analyzing and communicating the model results. In the previous course you learned how to derive the mass balance statements. Now we will proceed to derive rate expressions. Rate expressions are mathematical formulations of each flow, so the import and export fluxes that determine changes in the state variables of interest. In contrast to developing mass balance statements, rate expressions are a bit more difficult to conceive, as you need to incorporate reasoning from theory and/or empirical insights from the system of interest to move on efficiently. Rate expressions are typically a function of state variables that you defined earlier, but also the forcing functions that impact these fluxes and static parameters that control the model processes but do not change with the model. Atomic weights, gas constants, and interaction strengths are examples of such parameters. In this course, we will take a closer look at how to express ecological and chemical interactions. Let us first start with chemical reactions. Here, rate expressions are typically derived from the mass action law, which states that rates of change in chemical reactions are proportional to the power of the coefficients, with powers being the stoichiometric coefficients. Consider, for instance, a chemical interaction between one molecule A and 2 molecules B, eventually reacting to molecule C at the rate m. This is an example of a third-order reaction. The mass action law then states that the rate of this reaction equals m times the concentration of A times the concentration of B squared. With changes in A and C, respectively, the negative and positive rate, and the change in B being twice the rate but negative as B is disappearing from the reaction. Or for a more complex enzymatic reaction, with enzyme E transforming D in I, and I further reacting into the enzyme E and F. The reaction from D to I is reversible. The reaction thus consists of 3 rates that can be expressed in rate 1 being K1 times E and D, rate 2 being K2 times I, and rate 3 being K3 times I. This gives as mass balances delta D on dt equalizing rate 2 minus rate 1, delta I dt being equal to rate 1 minus rate 2 minus rate 3, delta E dt being minus rate 1 plus rate 2 plus rate 3, and finally delta F on dt equalizing rate 3. Or translated into the eventual differential equations, this gives the following, with for instance delta D on dt being minus K1 times E times D plus K2 times I, and for delta I on dt being equal to K1 times E times D minus K2 times I minus K3 times I. Put into a graph, you see that any increase in F is eventually accompanied by a joint decrease of the concentrations D and I in the interactions, as they are the fuel for the production of F. Now, what about ecological interactions? These are, for instance, nutrient uptake by grazing, predation, or parasitism, and in typical cases such interactions are mediated by an active partner in crime, the predator or the consumer that is effectively performing the action, preying or consuming, and the partner or compartment that is subject to this action, so the prey for the predator or the nutrient pool for the consuming algae, for instance. Units for these interactions are typically in the form of density or concentration per time. The interactions can, however, not proceed infinitively. They are constrained by, for instance, the physiology or the available time of the worker. The maximum rate thus indicates the maximum amount of resources to be processed per time unit. The maximum amount of work done in the system is therefore equal to the max rate times the abundance, density or biomass of the workers in the system. Moreover, when the resources are lacking, then no interaction can take place. The interaction will therefore always be determined by a rate limiting term, that is a function of the resource availability. If resources are absent, then this term and the entire interaction will be zero. The interaction is thus always a product of the max rates, the worker availability, and the limiting term, which on its own is a function of the available resources. So for predation, ingestion equalizes the max ingestion rate of the predator times their availability times the limiting resource uptake function. For nutrient uptake by algae and other plants, the same principle holds, and the eventual rate will be a product of the maximum uptake rate, their abundance, and the limiting term again. The interaction is thus composed of a flow, a constant parameter specific to the worker, and the two state variables. The parameter always has per time as a unit. The limiting term is unitless, and together with the concentration of the workers, the entire interaction function has concentration or density per time as a unit. The rate limiting terms are in an ecological context typically defined as functional responses. These functional responses define how a consumption rate is affected by the resource availability. They should not be limited to a single limiting resource. They are dimensionless between 0 and 1 and related to the behavior of the worker. We typically recognize three larger classes of functional responses: type 1, type 2, and type 3. A type 1 functional response is characterized by a linear uptake till a maximum. It therefore represents a random sampling strategy of prey that are available in the environment, and is therefore often referred to as a blundering idiot strategy. Filter feeders like mussels or this very nice garden spider show typically such a functional response. More active hunters like this wolf will become constrained in consumption of prey by their handling time. We refer to such responses as type 2. When the resources are low, consumption will be more or less linearly increasing. But when the resources become abundant, consumption rate will level off simply because of time or energy which is lacking. The shape of the functional response is determined by Ks, which we call the half saturation constant. This constant represents the concentration or density of resources at which consumption is half of the maximum intake rate. Type 2 responses are also referred to as the Monod or Michaelis-Menten function. Finally, when consumers or predators need to learn where to find prey, consumption will be low at low resource levels, but rapidly increasing when some consumers have found their victims. Think for instance of sharks being attracted by smell of the first few attacked fish from a big school. This functional response is of type 3, is sigmoidal, with its steepness determined by the steepness parameters in the power of all terms. When more than one resource type is limiting, then both limitations are considered. These can take the form of the eventual uptake being limited by the one least in supply. Think for instance of plants being limited by the lowest level of nitrogen or phosphate. This is what we call the Liebig law of the minimum. Second, both limiting factors may be multiplicative, so strengthening the eventual uptake. Algae need for instance both lights and nutrients to grow. Finally, resources may be subject to preference of the consumer. In this example, two resources are preferred at rates P1 and P2, and these are additively included in the functional response. Without preferences, P1 and P2 are 1, and both sum to the total resource availability and need not to be defined separately. Alternatively, one component may inhibit the uptake of another one. Nitrate uptake by algae is for instance inhibited by ammonium. Here, the inhibition is included to the rate expression as a negative exponential function, so defining an exponentially declining nitrate uptake with increasing ammonium concentrations in the water column. In biochemical models, rate limiting terms can be a function of the source compartment, for instance in the process of hydrolysis. Here, bacteria perform the action of transforming semi-labile dissolved organic carbon with large molecular weight, this is the semi-labile DOC, to low molecular weight dissolved organic carbon. The hydrolysis rate is therefore a function of the semi-labile DOC that needs to be hydrolyzed and the availability of the bacteria, that are the workers here, in between two states of the organic carbon. Units are, as for the earlier seen rate limiting terms, defined as either concentrations per day, rates per day, or concentrations. So far, rate expressions have been used to link variables by flows. They may, however, also be used to couple different flows. In the below predator-prey relationship, the interaction not only provides a carbon flux from prey to predator, but also to detritus by defecation and to CO2 by activity respiration. All these relationships are related as an organism cannot produce more feces than the amount of food ingested. So, while ingestion rate is a function of the maximum ingestion rate, the predator and the prey availability, defecation and respiration will be direct functions of this ingestion rate. The final amount of assimilated carbon in the predator's stomatic tissue is then the net balance between ingestion, defecation and respiration. This activity respiration is also referred to as growth respiration, as it is known to increase with the amount of food available for assimilation. And the eventual transfer of C from ingestion to CO2 will be a fraction of the assimilation, here referred to as the constant growth cost. Now, putting equations together, you will notice that the differential equations for each state variable are coupled, and that fluxes defining sources to one compartment may function as sinks to another one. In our example, these coupled equations will provide feedbacks that stabilize the system. Increases in prey biomass will lead to increased predator pressure and hence reduced prey biomass. This lower prey biomass will then cause declines in predator biomass, such that the prey biomass may recover again. Feedbacks thus induce coexistence between the two antagonistic compartments. Finally, many stoichiometric expressions are also tightly coupled because degrading processes of complex molecules, for instance the respiration of several elements from organic carbon matter, occur at remarkably constant ratios for all elements. These ratios are referred to as the Redfield ratios. Stoichiometric ratios for C, H, O, N, and P are, for instance, 106 to 263, to 106 to 16 and 1. This means that, for instance, for 106 mole fresh algal organic matter, 106 moles of oxygens are consumed, while 16 moles of ammonium and only 1 mole of phosphate become released. Interactions can thus be highly complex if all compartments and their interactions are considered. Modelers do, however, have tricks to simplify them as much as possible. If resources are unlimitedly available, we may, for instance, decide not to represent them as a state variable and to model the uptake by consumers as a constant rate. Similarly, when the focus is on the lower trophic levels and predators are always present, we may simply model predation by a mortality closure term. When certain compartments facilitate transfer of matter from one to another, we might simplify these linear processes and replace them by a single integrated flow. And finally, as often used for biochemical reactions, we might, as for the resources in ecological interactions, keep one compartment always constant in the flow. In contrast to the usual linear and hence constant uptake rates of producers by consumers, mortality rates can be modeled by quadratic terms as well. Such a quadratic closure terms then indicates that predation rates increase with prey biomass. Although the use of this function is under question, it reflects a nonlinear increase in consumption with prey biomass, either due, for instance, increased predator biomass or increased predator growth under prey-rich conditions. An example of neglecting the working compartment is typically the action of bacteria hydrolyzing organic carbon that has been released from detritus. If we assume bacteria to be constantly and abundantly available, then this entire chain can be shunted into a mineralization flux. And as mentioned earlier, consumed state variables can be constant as well. For example, we can replace oxygen consumption as a direct function of the organic matter to be oxidized, so neglecting the unlimited and hence constant oxygen concentrations. A final and very commonly used simplification is the introduction of carrying capacities to the model. These are used to model density-dependent competition processes, eventually leading to stable maximal population sizes. In ecology, these maximally attained population sizes are typically referred to as the carrying capacity of the system. They thus indicate the population size where populations or biomass growth rates are 1 and where populations stay stable over time in size. The term 1 minus predator abundance on K is here included to the equation to make this growth rate dependent on the density or abundance of the predators, or more generally, the workers. In addition to these coupled flows between state variables, both state variables and the fluxes can be conditional to the external physical conditions. These can, for instance, be a function of temperature, think of oxygen availability in seawater, or many metabolic processes that are temperature dependent. Be a function of light or radiation, think of photosynthesis, energy availability, or a function of wind, exchanges of gases, for instance, at the sea-air interface or the spread of seeds. In all cases, these forcing functions are implemented from coupled mechanistic algorithms or recorded data. The last step in the process of model formulation is the consistency check. We have already introduced this in the previous course, but as this is an essential step, especially when complex models are built, we reiterate this here. Now that we formalized the rate expressions, unit consistency poses an uttermost valuable control mechanism on the model formulation. Of course, and in conjunction with the earlier outlined check of energy and mass conservation. The premise of this unit check is simple. An equation is homogeneous, so correct in terms of its dimensions, if they match at both sides of the equations. Units can be defined by the international standards, meter, kilogram, Kelvin, mole, seconds, or examples. They can also be derived from these standard units. Celsius is, for instance, the standard temperature unit Kelvin, minus 273.15. Force is expressed at kilogram times meter per square seconds, or more simply, Newton, and energy is typically expressed in Joule units, which represent kilogram times square meter per square second, or newtons times meters. This means that in order to check whether units match on both sides of the equation, they can be manipulated as we do with numbers. For instance, Joule per kilogram can be transformed in squared meters per square second. Of course, remember you cannot add different units. Adding mass to length or even grams to kilograms is just impossible. This sounds very basic, maybe even secondary school material. But from experience we can guarantee you that most errors in modeling occur simply by the use and calculations with inconsistent units. As an example, changes in concentration in detritus have always as unit millimole nitrogen per cube meter. Rates only a per time step unit, here day, and phytoplankton concentration of carbon are typically expressed as millimole carbon per cube meter. In this equation, all looks good at first sight, but essentially you're simply comparing or relating apples and pears, nitrogen and carbon, so this is clearly an inconsistent equation. Finally, we also need to bring the mass conservation again under attention. Remember, this check is based on the sum of all rates that should either be zero in a closed system or the sum of the export and import flows when external transport is modeled. We now go through an entirely worked out example. We chose nitrogen cycling in a marine bay. The nitrogen cycle is one of the most important biochemical cycles on Earth, both on land and in water. While it may be quite complex, involving many compartments and reactions, we will develop a simple cycling based on the following conceptual scheme. Dissolved nitrogen is uptaken by phytoplankton, for which concentrations can be easily monitored by measuring the greenness of the water column, by measuring the chlorophyll content thus. Phytoplankton is consumed by zooplankton, which in this case dies off for the moment by undefined processes, becomes detritus, wherefrom nitrogen can be released again into the water by bacterial activity. All living organisms excrete nitrogen, and its uptake by algae can only occur when solar light is available. The mass balances are simply the net fluxes. So for change in phytoplankton, they are 1 minus 2. For nitrogen changes in zooplankton, they are 2 minus 3 minus 4 minus 5, and so on for the changes in nitrogen in detritus and the dissolved nitrogen. Now the rate expressions. Grazing is a function of workers, resource availability, and the maximum attainable grazing rates. We here assume a function to response. Such responses are actually most often modeled. Excretion is a simple linear relationship of zooplankton biomass, and feces production is linearly coupled to the magnitude of grazing. Predators of zooplankton are not considered, but we assume them to be present ad libitum. Therefore, mortality of zooplankton is only a function of their own abundance. and N is instantaneously transferred to detritus. Finally, N uptake by algae is limited by both the availability of photosynthetic active radiation, PAR, and its availability in the water column. We formulate this uptake then in function of the minimum availability of either the radiation or the dissolved nitrogen. We also need to perform a consistency check. We here give the one for grazing. If you pause the video and take some time to digest the equation, you will see that this rate expression is consistent as both the left and right hand side equalize to millimoles nitrogen per day per cube meter. The same holds for mass conservation, as already demonstrated in the previous course. And now it's up to you. We have prepared a variation of relevant examples, from further developing the salmon-bear carbon cycling over ozone dynamics in the atmosphere, virus dynamics, detritus decay, towards competition between plants on land. Enjoy and learn a lot.